Here we'll see how we can model the plate with the cutout and how we can analyze the how is the pattern of stress concentration. So to do that, what we're going to do here, first create the geometry using part. So here we'll select create part options and we select 3D geometry, cell and planar. Since our maximum size is 100 mm, so here we are choosing as 200. Now we choose this option, rectangular option. Now here we'll define first corner. So I am defining first corner as -50, -25. It is your one extreme left corner, and then we'll define the extreme right corner. Now in this way we can create the rectangular plate. Now you can choose the circular option, and here you can see it is asking pick center point. So our center point is 0, 0. Now it is saying pick a perimeter point. So our perimeter point is 10, 0. Now here you can see we have created a plate. We have created a rectangular plate with a circular cutout. Now what we are going to do? We are going to click on done. You can see we have created a plate with circular hole. Now, what we are going to do? We have to do the meshing, but there we have to do the meshing in such a way that we have finer meshing here and we have finer meshing. We have finer meshing here and we have coarser meshing this side. Okay, we have finer meshing near the stress concentration zone and we have coarser meshing little bit away from the stress concentration zone. Okay, so to do that, what we have to do? We have to create some partition here. We'll create the partition in a symmetric manner. To do that, what we can do? We have to create some point here, here, and here. 4 point we have to create here, and we have to join that point so that we can have a symmetric point. Since we do not know, at which point we should select, since we do not know which point we should select. Now, what we are going to do? We are going to choose this option. This option is basically create a term point. Here, if you give a long press, you can see you have a lot of options. So here you have to choose this option, and from here you have to choose this point, and then opposite corner here. Similarly, again you have to choose this point, and you have to choose this point. Now here you can see we have created some point here. The intersection is basically a point here. Now we will choose partition options to create symmetric partition. We'll choose partition options. So here we'll choose this partition option. Now we'll choose this partition option. Okay, now it is saying select an edge or axis. So we'll select this edge. Now we can see that we have many options. Now from here we'll choose this option and we'll choose this point and this point to create partition here. Again, we'll choose this corner to this corner. Again, we'll choose this corner to this corner. Again, we'll choose this corner to this corner. Okay. Now we'll click on done. Now here you can see we have created 4 part 1, 2, 3, 4. Okay. Now see both. You can see this is very symmetric. You can see this is very symmetric. This part and this part is symmetric. This part and this part is symmetric. Okay. Now what will you do? We have to define the meshing. Okay, we have to define the meshing. So to define the meshing, what we have to do? We have to go to assembly and then we have to click on dependent type instances. In the assembly, we used to create instances. So here we will create independent instances where we can do the meshing on the part. Now we'll go for meshing and here we'll choose this part option and we'll define the meshing. Now to define the meshing, what we have to do? we have to first create the seed value. Okay, and then we have to do something such that we can have finer mesh near the stress concentration zone and coarser mesh the other side. Okay, so basically what we are saying that our meshing should be biased towards the stress concentration zone. So to do the biasness, we'll choose bias option. We'll see how we can choose that. Okay, so first we'll define the seed value, and then we will define the biasness, and we will see what type of meshing we want to do. So now we will go for seed value. Seed value we can define by two ways. One is use global seed value, but here we'll choose this option seed by edge. Okay, seed by edge. Here we select this edge and this edge. We define seed value as a 40 here. We define seed value here 40. This side and this side will define seed value as we said is 40, and sorry, this side and this side will define seed value as 40, and this side will define the seed value as 80. Okay, and here we'll define the seed value as 40. This side will define seed value as your 20. Here also similar, but here we have two segments. In the first segment, we'll define the seed value as 10, and second segment also will define the seed value as 10. Okay, now we have defined the seed value. Now what we will do? We have to define the biasness. Here we will choose this line and we will define the biasness option. So here you can see we have bias option. Here we will choose this single bias option, and you can see the arrow here. Our arrow is here outward, but that should be inward so that our meshing will be biased towards the hole. Okay, so here we will do flip option, define the biasness towards the hole. Here also this is fine. This side will see this is opposite in nature. Here also will define the biasness towards the hole. Here also will define the biasness. Okay, now we have defined the seed value and we also have defined the biasness. Now we have to see what type of element, what type of meshing we want to do. In this case, we want to define structure type meshing. Okay, you will see in ABAQUS we have various type of meshing. We will have various type of meshing. So here to control over the meshing type of meshing, we can click on control button option and then you can select the geometry. Then we can select the geometry. Now what we can do, we can see what type of meshing we have. We have free meshing, structure meshing, sweep meshing. For this case, we want to define structure type meshing. So here this part and this part is green, so this part will be of structure type meshing. We want to define this meshing also as a structure type. So here this meshing also as a structure type will define like this. Okay, now what we have done, we have defined that type of meshing. We have defined type of meshing is our structure type meshing. Okay. Here you can see the structure type, it is saying quad dominated. That means all meshing will be rectangular type. Structure meshing is basically quad dominated, means wherever possible it will create four noded element here. Okay. Now what we are going to do, we are going to go for meshing. Now here we select yes. You can see there is meshing. You can see our meshing is finer this side. Okay, finer this side. Okay, finer near the hole, and when you go away, you will see our meshing is coarser near the edge. Okay, finer near the hole and coarser near the edge. But here you can see this meshing size meshing is not good. It's very poor type of element is showing. See one element here, you can see this element is very long. So this is basically one poor type meshing. What we can do, we can define the seed value such that we can have a good meshing here. Okay, We'll see how we can do that. We'll select these options here. We'll define here. We'll define for 20 here is fine. This side also. Here this side we have to define 40. So here we have to define the biasness. So what we are going to do, we'll select this option, we'll select this line, and then here we select this is biased towards this side. Okay, a number of element we can make it is 20, or you can say make it is 40. All line similarly, we select all the line, we'll see whether okay, this is your arrow is along this side. Arrow is along this side, so biasness is fine. Here also limit number element is 40. This side also. If you observe that this arrow is in opposite in nature, then you can click flip option so that you can choose correct biasness. Here also we'll choose and we'll have element 40 number of element this side. Here this also you have to choose with the 40 element. Here we have defined the biasness. Okay. Now we have created the seed. We have defined the biasness. Now what we are going to do? We are going to choose what type of meshing we want to provide. By that it is rectangular meshing or triangular meshing. That meshing we can choose. So here if we have options, we have option of control meshing. Here we have the option of control meshing, assign control mesh. This option, if you have to click this option, you have to select the body. And if you click it here, you can see by default it is coming as free mesh. Okay, now here we want to select the structure type meshing. We want to select structure type meshing where we have quad dominated meshing. Here also we'll have quad dominated meshing. Here also we'll have quad dominated structure meshing. Here also quad dominated structure meshing. This part also will have quad dominated structure meshing. Now we have defined the seed value. We have defined the biasness. We have defined what type of meshing we want to do. Now we'll go for meshing. Here if you click on part, select the body, or if you click on yes, you can have a meshing. Here you can see our meshing is very fine near the circular cutout, and we have coarser meshing when you go away from the circular cutout. Okay, so we have circular mesh, we have finer meshing, near the stress concentration zone, and we have coarser meshing near the edge. So this is the way we can define the meshing. Now what we do, we have to define the material property. We have to define the material property. Okay, so to define the material property, here we can define material, and then modulus elasticity. In the elasticity, we have to define Young modulus. The elasticity define Young modulus to E5, and then Poisson ratio is 0.3. Basically, this is 200 GPa. If you convert it, it will come to E5 MPa in Newton mm unit. Now here we select cell homogeneous. We'll define the cell thickness as 5 mm. Okay, and now we'll assign material property and the thickness here. Here you can see the color has changed. That means we have defined the material property correctly. Okay. Now we have to go for step. The step here we just remember the step we used to choose what type of analysis we want to perform. The step we used to choose what type of analysis we want to perform. So here if we're going to define what type of analysis we want to perform. So here we want to perform static analysis. So we'll click here and then we'll go for static general. We'll choose the default value here and we'll apply the loading here. We'll apply the load using these options. Now we'll apply the cell edge load. Now we'll select this cell edge, we'll select the cell edge, and now we'll apply here 100 minus 100 magnitude and then ramp conditions. Okay, so here you can see we have applied the loading here. Now we will apply the boundary condition. We will apply the Ancaster boundary condition. We will choose this edge and we will apply Ancaster. Ancaster is basically one boundary condition where all degree freedom are constant. U1, U2, U3, UR1, UR2, UR3 are constant. U1 is corresponding to displacement along x-axis, U2 displacement along y-axis, U3 displacement along z-axis, UR1 is a rotation about the x-axis, UR2 rotation about y-axis, UR3 rotation about z-axis. So all degree of freedom are constant. So we have defined all the things. Now we'll go for job and we'll submit the job. We'll submit the job as your plate circular cutout. Plate with circular cutout. Now we'll submit the job. It will take some time. Once we get the result, once the job is completed, we'll see what are the deflection is coming. Once we see, okay, now job is completed. And here you can see the displacement. Here you can see S11. Here displacement we will see S11. So you can choose this option XY plane. XY plane, if you plot, here you can see that maximum stress is occurring here. Maximum stress is occurring here, and value of this maximum stress is 1.82. It is 1.82, and here also you can see stress concentration is occurring here. Okay. Now you want to see what is the displacement is coming and what is the reaction is coming. If you want to see what is the deflection is coming, what is the direction is coming. Now you have to do some. We have to request ABAQUS. We have to request ABAQUS for reaction forces and for the displacement. You have to request ABAQUS for the reaction forces. So here, if you want to define, if you want to request for the reaction forces, if you want to request for reaction forces, then you have to go to tool and then you have to go to create options. Then you have to create node set. Here you can define this is reaction force RF, and you can choose all the node here for which you need the reaction forces here. Okay, and another set you can create for displacement, and here you can write displacement. Now we choose all the node here. Okay, and make it done. Now we have basically defined the node set for reaction force and displacement. Now what we'll do, we'll go to the step. Now the step will go in history output. In the history output, we'll write reaction. And here instead of whole model, we'll choose set, and then we'll choose RF. And here we'll ask to find RF1 because we are applying the load in the x direction. So our reaction also will come in the x direction. So we have to choose RF1. Then again, you have to go to your history output. You have to set this. You have to choose set, and then you have to choose displacement. And from the displacement, you have to choose U1, and you have to leave it like this. Okay. Now, what we can do? Now we can again submit the job and run the job, and we will operate on the XY data to plot load versus displacement. Load versus displacement. That is completed. Now we go on the create XY data. Here we choose ODB history output because we have given the comment on history output. In the steps, we have given the comment in history output. So here we choose RF2, and here we save it as a sum of reaction. Okay, and here we'll see how much load we applied. So we have applied 1,000 load. We have applied 1,000 load. Okay, we have applied 1,000 load. Okay, so here you see how much load we applied. Here 100 it is showing. 100. Okay, but reaction force is showing 183,000. How? Two nodes. So we have divided 100 divided by 41. So each node we have 2.43. So why it is showing? Why it is showing? When you take energy 0, internal energy high, all energy, all work energy, external work. Kinetic energy all K, which is static energy. Okay, fine. At Y for reaction force RF2, we have applied that load as 100 Newton, 1 to 2. Okay, but reaction force we are getting as 1000. How? Okay, okay. Thickness is 10 mm. 2 mm thickness. Acha, so total force is basically 100 into 2 into 50. 10,000. Then it's come 10,000. Only 1,000. No, 5 to the 3, 5 to the 3, which is 5. Fine, ठीक है. UDL load 5. अच्छा, ठीक है. Okay, okay. Now we have defined the history outpost, and now we have defined node set for displacement and node set for reaction forces, and I also have requested the steps. The steps we went to history output, and then we requested displacement for particular set and reaction force of a particular set. Okay, now what we will do, we will try to see how much reaction force is coming. So here we'll choose all the reaction force, and here we'll choose all the reaction force. Here we'll use shift button. Here. We'll save it as a sum, and we'll write RF. We'll write it RF, and we'll save it. Okay. And next, what we are going to do, we are going to use this displacement content, and here we will choose save as a average displacement. You can write, and you can save it. Okay. Now here you can see displacement is increasing from 0 to 1 time. Maximum displacement is 0.03. Okay, now again we'll go there and then we'll select on operate XY data. And now we'll choose combine option. Now here we'll choose displacement. Okay, and then we have to choose minus sign because reaction force was coming in negative order. I'll plot it. Okay, now we will plot it. That is not taking displacement. How to choose that displacement? Here you can see force is changing in negative order. So here you can give minus sign and then you can plot it. Okay, this way you can plot. Okay, now here you can see. Now here you can see. Okay, now to plot. Now to plot. Now to plot x. Now to plot force versus displacement. Now what you have to do? You have to choose combine option. You just choose combine. You just click once the combine option, and then give one click on displacement, and then reaction force. Okay, now you just plot it. But here, see reaction force. The force is coming in negative order. You can choose. You can give minus sign here, and again plot it. Here you can see this is your force versus displacement. So your maximum force is coming 5E3. 5E3 means 5,000. That is also same as your applied loading. So we have total load of 50 mm and we have applied 100 load. We have applied 100 load and your width is 50. So total load will be 50 into 100, so 5,000. That's fine. Our force is 5,000, it's fine, and displacement is occurring in 0.03, 0.030 mm. Displacement in 0.03 mm. Okay, so this is the way we have to plot the load versus displacement. Now, if we see our deform shape, if we see the deform shape, okay, if you see the deform shape here, then here you can save this also. If you want to see, if you want to plot it, if you want to save this, okay, then what you can do, you can go to options, then you can go to common option. From here you can delete the edges. You can temporarily suppress the edges. Here you can select 3 edges. You can click here, apply. Here you can see we are removing all the element connectivity, all the things. Okay, we are basically suppressing the edges. We can get a smooth contour. Okay, to get a smooth contour, what you can do, you can go to options and you can click on common, and here you can choose 3 edges. Okay, you can see we can have a smooth contour of your deform shape. You can save this one. You can go to the print and you can go to the file. You can go to the file and then print options. From here you can save it as a file, and you can give some name, plate, something like that, plate, and format you can choose PPP or TIF format or PNG format. You can choose TIF format, TIFF format, TIFF format, or PNG format. Okay, now we can see. Now we can see the temp. We have created a file. Go to the C drive and you can go to the temp folder and you can select plate. Here you can see we have created the We have created the file with a stress distribution. Here you can see stress distribution is coming in symmetric. Here you can see stress distribution is symmetric. Symmetric in the sense our boundary condition is symmetric, loading also symmetric. Boundary condition is not symmetric. One end is fixed, other end is free. It's not in that way. It's not symmetric, but structure is symmetric and hole also symmetric. Due to that, our stress pattern is coming symmetric. Okay, so here you can see our stress pattern is coming symmetric in nature. So, so you can say our analysis is fine. Our analysis is fine. Okay, now to see whether result is converged or not, see whether result is converged or not, what we have to do? We have to go for final meshing. So what we can do? We can choose this seed by, we can choose this seed by edge. Okay, you can choose this seed by edge. Okay, and then you can go for final meshing, and then again you can analyze it, and you just take that down. You just note down the data, displacement or stress concentration is at your stress concentration is your objective. So what you can do, you can go for final meshing, you can go for final meshing, and then you can note down what is the maximum stress is coming here, and you can note down the stress, maximum stress which is occurring. You can note down the element number and the maximum stress is occurring. So you can have 2-3 trial with the increasing number of element and see that up to which element you can get converged result. So this is the way you have to do the analysis for a plate with hole. Here we learn how we can plot the stress along the width of the plate. So what we can do, we have to follow 2 steps. In the first step, we have to create path, and in the second steps, we have to plot the stress along the path. In the second steps, we will plot our variable along the path. So let us do it. So go to the tool, and here you create path. Go to tool and then path and create. Now here create path 3 here, and here you can click add before or add after, whatever option you want to choose. Just click on add before and select this is your as the first point, and this is select this one as your second point. Okay, now click on done. This is the way we can create the path. Now what we have to do? Now we have to go to visualization, and then you have to go to create XY data, and here you have to click on path and then click on continue. Here you have various options that you can play with. Now here you can choose deform or undeform. Here you can choose the value as a true distance or normalized distance. What are the value you can choose, that you can choose, and here you can choose at which loading. That means at which step you want to plot the variable. Okay, and next is our field variable, and variable here our S11 or sigma 11. So here on this option you can select S11. On this option you can select S11. Okay, now you just click on. So this is the way we can plot. So now here you can see. Now here you can see this is basically variation of the stress, variation along of the stress along the width. So if we save it and if we rotate it, then it will be easy for us. So let us save it as a stress path. Replace it. Now what we can do, we can open the plot, and now you can rotate it. Now here you can see this is the location of our cutout, and here you can see this is the maximum stress that is occurring here, and here the stress is basically from here stress is basically gradually decreasing. This is the stress that initially we have predicted. This is the stress. This is the magnitude of the stress. This is the magnitude of stress that initially we have predicted that if you have a cutout, then there will be stress concentration. So this is the stress here, which is concentrating near the cutout, and once we gradually go away from the cutout, our stress is reducing. Okay, this is the way we have to plot the stress along the path. We can plot the stress along the path.